Our first talk in the afternoon is by Mikhail Bershtein, and he will talk about chiralization of cluster structures. Welcome.
Thank you. Is my microphone working? Hope so. Okay, so I would like to thank organizers and BIMS in general for organizing this big school and conference. I'm going to report about work, or maybe it's not a work, like a project in progress, and with a number of courses: J Shiraishi, J E Bourgine, Feigin, Shapiro, and G Schrader, who probably will be here next week. And the goal of this project is connection. Connection between two fields, and it's, I think, quite clear from the title. So one of this part would be cluster. I will put those structures, meaning that could be cluster varieties or cluster algebras, both. And on the other side of this arrow will be some representation theory. But this word chiralization means it will be representation theory of some infinite dimensional algebras, like infinite dimensional algebras. The first approximation one can think about vertex algebras, like W algebras or affine the algebras, but since cluster structures are in some sense multiplicative, so practically here will be Q-deformed. We will live in Q-deformed setting. So instead of standard W algebra will be like QTW algebras. The affine algebras will be replaced by affine quantum groups, and more elaborate stuff like toroidal algebras also appear here. So as I said, the goal to establish connection. This is in progress, so I will state some theorems, and I believe all theorems which I state now have recent proof, but please take care. My goal is to present some idea at least, but the idea which is, at least I believe, is new is really concerns the part which is chiralization, when we come to the infinite dimensional algebras. And actually connection between cluster structures and fine dimensional quantum group is somehow established now, and I start with establishment. Let me first recall a bit, at least partially, what are the cluster structure, what is a quantum cluster algebras. The cluster algebra starts with an oriented graph. And for beginning, I consider an oriented graph which is two vertices and one arrow. And then for each vertex, we assign a variable, say A and B. And arrows encode commutation relation between these variables. So if we have one arrow, then relation is AB is equal to Q squared BA. And more generally, if we have a huge graph, then commutation relation between variables, say xi and xj, will be Q in power 2 Bij xj xi, whereas this Bij is number of arrows from I to j minus number of arrows from J to I. It's allowed, but it doesn't affect commutation relations. So you can cancel cycles of length 2 before we come to chiralization. In chiralization, that would mean something. So practically, algebra which we defined now is just sometimes called quantum torus. So this algebra of polynomials on some variables x1. It's usually considered polynomials considered to be Laurent polynomials, subject of such Q commutation relation. Sometimes it's called quantum torus. Of course, these algebras are very simple, and first connection with algebras like quantum group is that we can make representations of the quantum groups using these quite simple algebras. The simplest example is the following. Consider the following quiver. Maybe draw arrows using some colors. So there's a quiver with 4 vertices and actually 4 arrows. And we can define the following expressions. E is equal to x1 plus, okay, let me write x1 plus then these generators, E, F, K, and K prime, they satisfy quantum group relations. To be more precise, here they satisfy relations of the Dirichlet double of the Borel subalgebra. But if you impose that K times K prime is equal to 1, if you take the corresponding quotient, okay, you should make product in some order. Then you get standard UQ SL2 algebra. Of course, you can think that these formulas are quite random. I tried to represent something by colors. So when I define E generators, I somehow go along blue lines. So if I go with colors more seriously, then this E and K correspond to blue part of this graph, and K prime and F correspond to red part. So K is just a product of variables along this line. And E is some telescoping sum, it's first, plus the product of first and second, and it's just and similar for Fs. Since this is partially school, I'm trying to be elementary at the very beginning. Oh, thank you. Organizers applied me the clock. One way to think about this is the following. So this algebra of Q commuting generators is one can think about this as an algebra of Q difference operators. So these formulas, so equivalently, this is a representation of, if you want, UQSL2 via Q difference operators. So one can take, say, x and difference operator d, which is q in power x dx. Then this operator q commute, and then one can realize, take representation of this quantum torus x1, x2, x3, and x4 in terms of x and difference operator. So like x1 goes to x, x2 goes to maybe the inverse. I don't know, so this is a formula, at least which is written in my notes, but something like this. And then you get a representation of whole QSL2. Maybe
That over here, x3 is x or lambda.
yes, exactly. So here you have additional variable lambda. So here we have 4 variables. I assume that some product of them is equal to 1, so essentially 3, and they are represented in terms of x and dx and one additional central element lambda, which is correspond, of course, to the Casimir of QSL2. So we have x, dx, and lambda, which is central. Other questions? Maybe, again, as an analogy, so this realization of quantum group in terms of Q-difference operator should be viewed as a Q-deformation of realization of just the algebra in terms of differential operators. So we have action of SL2, we have embedding of SL2 into differential operator on the line, given by formulas like E goes to dx, H goes to minus 2x dx plus lambda, and F goes to minus x squared dx plus lambda x. And then we promote them to Q-difference operators, and then we somehow denote certain product of the operators multiplication and Q shift and call them cluster variables. Up to now, I defined the things which correspond to one quantum torus, or more geometric torus cluster variety, to one chart. But perhaps the most interesting, most important definition in this definition of cluster variety is the definition of mutation, the separation of glue in different charts. So this is I'm going to define next. I'm not going to give full definition, but I do illustrative example. So assume that we have a piece in the quiver which looks like this. So we have 3 vertices, and we have arrow from A to B and B to C. Then we can do mutation in the middle vertex B. So mutation is, first of all, transformation of the combinatorial data, transformation of the quiver. So we get a new quiver in which all arrows adjacent to B will reverse orientation. And then we should close the triangle, draw arrow here. And this is also supplied with the transformation of the variables. A tilde, B tilde, C tilde. And these new tilde variables are given by the formulas. B tilde is just B inverse. C tilde is C1 plus QB inverse. And A tilde is A1 plus QB. So I'm not going to check this, of course, on the board, but here I already made statements could be wrong. So I stated that if you define U, A tilde, B tilde, C tilde by these formulas, they would satisfy a Q commutation relation, which follows from this quiver. And I hope I didn't make a mistake, but this, the good property of this, of the formulas for E, F, and K, K prime, which I wrote there, is the following. So the property the generators of UQ SL2 maybe quantum group remain are Laurent polynomials after mutation. This is not obvious. So before I said that for any chart we have the Q torus, like Laurent polynomials, and these x variables. When we multiply, we have some Q power. But due to this inverse, this is not, we have no map between. If we have some function Laurent polynomial for one quiver, then after mutation can become not Laurent polynomial. But formals this property holds. And I don't know, I stated for one mutation, but actually for any sequence of mutations, they remain null. Of course, I mean, to make the statement very precise, I need to say more true that actually these two vertices are assumed to be frozen, so it is not allowed to mutate in them, but it's allowed to mutate in these two. What is the rule for these formulas? There are different answers. So first answer is the following. So if I have any other vertex which connects with this B with an arrow, I should multiply by like this. And if I have in opposite way, I should multiply like this. So if you don't have double arrows, this is already the definition. And for double arrow, you multiply something like a square of this. But for square, of course, you should shift argument by differently. For other quantum groups, we have to write larger quivers. For example, if you want SL3, there are two quivers, but okay, I want to draw them, but it would take a bit more time and space. So the number of vertices in quiver, they geometrically would correspond to dimension of the corresponding manifold. So here we realize quantum group like differential operators on P1, and we also have some Casimir. So actually, the dimension of the quantum group SL3 is 3. Or different double is 4, and then the number of vertices will grow quadratically. Here we more naturally realize the infill double, so it will go like n squared plus n. I don't know. Okay. No, I'm going to make more comments. I don't know in which order. So when I start to, there is another way to think about this formula that maybe represented using another color. So these formulas, they can be viewed as a conjugation by quantum dilogarithm phi of b, which is a 1 plus qb, 1 plus q cube b. Maybe it's readable. Product 1 plus q in power 2j plus 1 b. So the most essential part, this non-monomial part, transformation is given by this conjugation. And this also applies to some simple monomial transformation. Okay? Any other questions? Sorry? One of the definitions follows that the algebra of Laurent element of Laurent polynomials, which remain Laurent polynomials after any sequence of mutations. I am avoiding some technicalities, for example, difference between I don't know, a variables and x variables, and ask me later. Speed. So more geometric, one can think about this as the algebra of global functions, or of this quantization of algebra of global functions. And here it means that it corresponds to the fact that we represent, actually here, we represent SL2 as differential operators on A1, but actually they're differential operators on P1. So there is some additional constraint. We have another chart, like in second lecture today, and this is a post additional constraint on functions which we can write, differential operators which we can write. And we actually land to the differential operator which lives on the whole P1.
So the point is that we can say manifold and we count it with toy chart, and this cluster maps and conditions in this chart, then we quantize.
Yes, yes. Yes, a question? What? Yeah, so CTL is not Laurent polynomial, but combinations which we wrote above for E, F, and G, they remain Laurent. This practically is the reason why we take these combinations. Actually, I was told to repeat questions from the audience because people on Zoom, they don't hear. Please remind me to repeat it, or at least summarize. Other questions? I don't know, perhaps you can ask what's the logic of this queer, who told me this, and I'm not, so this quiver comes from some geometry of local systems on the surfaces for Goncharov's story, and secretly this quiver corresponds to the disk with puncture and 2 mark points on the boundary. And this puncture secretly lives here in the center. Of course, this is just one chart, or another. So doing mutation, we can come from this chart to others. For example, There is another chart which I like. Another chart. It has the following form. Like this. Maybe yes. Also some horizontal arrows here. And this quiver is now drawn, considered to be drawn on a cylinder. So there's some way to come from this punctured disk to the cylinder. And this way, there is some clever composition of mutations. In this case, just one mutation, but in general, it's a hard question to compare realization in one chart to another chart. But that's combinatorial technique to do this. Okay, let me once again ask, are there any questions? In SL2 case, these two pictures coincide, but actually there is, because you can do mutation, there is one more picture also. In SL2 case also you have freedom. And this would correspond to something non-trivial to formulas of your generator. So here, this realization symmetric, both E and F are sums of two terms. But if you do mutations, then E become one term and F becomes sum of four terms. So there is some room to play with difficulty of your formulas. Both formulas are, both pictures here are generalized for SLN, and actually there are more nice combinatorial pictures which can be generalized for higher rank. Yes.
Sure. In this picture, we have this number of columns or one less.
We have three full columns and two full columns, and one column is not full. Actually, if you add two additional vertices, we will get realization of not SLN but affine SLN in evaluation representation. Okay, hope there's no questions. I'm exactly in the middle of the
Sorry, what was the previous question?
So, question from the Zoom?
What was the question asked?
What was the last question? The last question was, what is the number of columns in this picture? On this picture on the cylinder. So this is a picture on disk, and this is on a cylinder. And the answer is that there are two full columns and one, and two is like n minus one full columns and one is not. Yes. So this, as variables on the boundary, they're usually frozen, and internal ones are unfrozen. Okay, now 31 minutes, so 1 minute more than a half, but still, maybe it's a good point to start the talk. And now explain about what I'm going to talk about. What is chiralization? Goal is the following. So we have realization of the quantum groups in terms of Lie algebra in terms of differential operators, or quantum groups in terms of difference operators. How about if we want affine Lie algebra or quantum affine algebra, how to realize it. And the in this not Q-difference case, such realization goes on the name of Wakimoto realizations. And in Q-difference case, perhaps they're also called Wakimoto. Here consider SL2 or entire paper. There are several papers in the 90s about formulas how to realize about Q-difference Wakimoto realizations. Formulas looks. Some expert told me that they are just horrible and they're total mess. And actually, I don't know because I looked on the first LN, but I think this method works for not chiral world formulas exist for any type, and I think this chiralization would work for any type, but I don't know. And if you ask, so perhaps the main idea is you can change, you can trade these formulas by the pictures like this, by this cluster combinatorics, but with some additional data. So the goal for the next, I don't know, like 10 minutes, give some idea how we're going to explain all these horrible formulas. So we start the same as we started here. We start with a quiver. And again, as a quiver, I consider quiver with two vertices and one arrow. And now the arrows will have some weights. Let me denote this weight by P. And to each vertex I assign, now it's assign a capital letter. And the fact that letter is capital means that now it is not one generator, but rather current of the form like A0 exponent of sum A minus n over n, where this A's satisfies some Heisenberg algebra. And commutation relations between now these generators are given in terms of operator product expansion, as usually in this signs. So we can write A of z b of w is equal to so operator product expansion is here is considered to be bosonic one. So I move all A's with negative indexes to the left and with positive indexes to the right. So here also assume to be operator product expansion. If you're not very familiar with this technique, so just ignore all the words about operator product expansion. If assuming that I'm trying to represent ideas, they would not affect idea. This is just normal ordering, bosonic normal ordering. Yes. This actually corresponds to singular part. So you have pole but I mean standard theory, the poles are contained on the diagonals like z equal w, and here pole is shifted by this weight of the h. The question of limit is delicate.
Maybe you should not use knowledge of empirical expansion. This is not expansion.
This is just normal ordering. No, no. Sorry. Yes. This is just normal ordering. Okay. Actually, there is one more formula. So this is here I defined commutation relations which correspond to arrow, but actually there should be one more formula which correspond to commutation relations which correspond to the vertex. Namely, if I take product of A of Z and A of W, it would be equal to, of course, normal ordering of them, but with again some functions. Before, for each vertex, we have assigned only just one variable. Of course, it commutes with itself. But now we somehow replace our manifold by loops to this manifold. So for each vertex, we assigned infinitely many variables. And after quantization, there is no reason to assume that they're commutative and actually natural choices here. Okay. So the first new feature, which you see here, is weights, which we assign to all ages. Yes.
Normal ordering is commute. Under the sign of normal ordering, you can commute A.
Yes. 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 Normal ordering is just normal of these bosons. Yes. Yes. It's commutative. This is normal ordering, yes. I said you can ignore normal ordering if you're not familiar with this, but in these formulas, now this one becomes meaningless. So just ignore these formulas. Or if you want, you can replace these formulas by formulas like this. The commutator of an and bm is equal n, p minus n, q in power minus 2n minus 1, delta n plus n, 0. So this normal ordering between A and B are equivalent to commutation relation between the Heisenberg algebras which correspond to the matrices.
What is the relation between A and A?
No, it follows from this. It will be something like q minus 2n minus q minus n plus 2 minus q in power 2n. Perhaps sine. It is not written in my notes, so written. Yes, exactly. Now I can write the left side also. This relation. Okay. Is there no more questions? I want to. So first thing which I wanted to comment was about these weights of the ages, p. How essential they are, and they're essential, but up to some extent. So first of all, there is. Okay. First of all, there is a group of there is certain gauge. There are certain gauge transformations of these weights. Namely, if we write namely, if we have some vertex, we assign to it some current, we can always replace just the variable z here by a of tz. Since we already live in Q world and we are okay with having poles and not on the standard diagonals but on shifted diagonals, there is no reason to prefer some choice of the variable. And this really corresponds, and if you look to these formulas, you see that here p appears near the variable of a, and here also the p appears near the variable of current a. So such transformation corresponds to the following gauge transformation. Okay, I don't know, a to the following gauge transformation of the weights. So if we have some vertex a with the weights p3, p4, p5. Why start with p3? Unclear. Then this transformation would just rescale the weights of these edges. So outgoing edges will have additional factor t, and ingoing edges will have additional factor t inverse. So corollary of this observation that weights itself are not important. What is important are monodromy around closed loops. Actually, at least in the examples, reasonable examples which we consider, there is additional constraint. Examples which you consider, they come from some geometric perspective, like for Goncharov, and the quivers are usually drawn on some surface. And on some surface, we usually have some condition. If you have local cycle, contractible cycle, then product of the monodromies should equal to q minus 2. And if you impose this condition, that essentially that your essential monodromies, you have essentially correspond to fundamental this commutative homology group of your surface. So, for example, in this case, the only essential parameter is the monodromy around this cycle. And here are the monodromy around cycle around origin. This additional constraint. I supported this constraint by, saying that it happens in examples which we have, but the most naive argument is the following. So if you consider quiver like this, then in terms of zero modes, it means that in the adjusted matrix we have zero, so the corresponding variables commute. But now if you Chiralize everything, whether they commute or not would now depend on their weights. And then it appears if you put weights p and q minus 2 p inverse, make their product equal to q minus 2, they corresponding currents would commute. So this is a way in which you can cancel out such thing. Any questions? No, not for two here. So the question was, is it constrained only for cycles of length 3? But the answer is no. For example, here we have a cycle of length 2, and also this constraint is good because in this way we can cancel. For any local cycle, if you have any phase on your surface, then monodromy around this phase should equal to q minus 2. Yeah. Okay, let me put it like this. This constraint which is satisfied in all reasonable examples. I think this is necessary for Laurent phenomenon, but yes. It's a matter of some conventions here. I mean, your poles are shifted. In one direction you shift by Q, in another in Q inverse. In order to cancel, you should. Short, I don't know explanation. I have no explanation. Just maybe it's a matter of convention. Okay, I have like 10 minutes left. Maybe it's a good time to state some theorem. Maybe not to state theorem. I need to repeat the draw again the quiver which I had draw on the left side, but still. So consider the following quiver. 1, 2. Okay, make it big. So again, this quiver is drawn on a cylinder, and we have horizontal arrows. And there are some arrows between frozen vertices which I'm not going to define here. So vertices on the boundary are frozen, vertices inside are unfrozen. Okay, and I forgot some red arrows. But up to now, this was a quiver just for before chiralization. There's no weights here. Yes. In principle, graph can be arbitrary. And in principle, graphs can be arbitrary. Better to have graph drawn on the surface, because on the surface, it's easier to work with this constraint. So this graph is drawn on a cylinder. Yes. And that graph was drawn on the, no, you know this graph. Okay. So up to now, that was the picture before chiralization, but now I have to put some weights. So I assume that use some gauge transformation to make all vertical weights equal to 1. Then I can make all horizontal weights to be the same, and they would equal to Q1, some number. And all diagonal weights will equal to some another number, which I denote by Q3. And these numbers satisfy Q1, Q square, Q3 is equal to 1. This is a condition for locality condition. So Q2 is Q squared. Just to ignore the problem with index up or down. And so the locality condition means that Q1, Q2, Q3, 1 this is equal to Q minus 2. Okay, theorem. Formulas like an example. Gives representation, and it's A of U, Q, GL3 toroidal in Wakimoto representation. I name this as A, means that I plan to make B, but maybe before some comments are necessary. So here we have toroidal algebra. This corresponds to the fact which I mentioned before. I added additional frozen vertices here and here. But essentially, this would just add me some additional Casimirs, which in terms of test series correspond to evaluation parameter. So essentially, this is evaluation representation. We have a map from toroidal to quantum affine, and then we take Wakimoto representation. But advantage of this picture is the following: that now we can, for example, glue this picture and construct representation of the toroidal, which are not irreducible representation of the quantum affine. More like product of evaluation representations is no longer irreducible representation of the fine dimensional algebra. Yes. For other types, I'm not quite sure about toroidal part. So I'm sure we'll get Wakimoto, there's quantum affine. But here, if you ask me, what was my reason to add these two vertices? I mean, for this picture, it's clear how to add them, but how to add them in the left picture, it's not quite clear. I mean, I know the answer, but I have no explanation. So I don't know about toroidal part. So you see these parameters like, so one parameter Q comes from quantization, and another parameter comes from this monodromy around this side, Q1. In terms of quantum affine algebra, if you don't like this toroidal, it would correspond to the level of your representation. Okay. And maybe it's good I can state B. This representation is mutation equivalent to known one. By known one, I mean some formals which are written in the matrices. This is new representation. I mean, as far as experts know, this is new representation. For example, this representation does have good limit when Q goes to 1, differential limit. But in Q difference, well, and I don't. Yes.
When you say that doesn't have a limit, it means it doesn't have a good limit to developing algebra.
Yes. I mean, for quantum groups, there are two limits to Poisson and for developing algebra. Yes. And perhaps I confused. Yes. Poisson limits exist. Okay. And perhaps at this point you can ask, what is mutation? I haven't defined mutation in this chiral world. And my clock has disappeared. Maybe it means that I'm almost out of time. and but I have my own clock, which says that I have 3 more minutes. So mutation. And as before, mutation consists of 2 parts. Combinatorial part, what happens with the quiver, and algebraic part, what happens with variables. And a combinatorial part you can easily generalize. So assuming that you have, say, A, B, C, the same query as above, you do mutation, and you just draw the same query as above. Actually, you can ask what happened with weights, and but you can see maybe it's not combinatorial part. But for algebraic part, you actually have a problem. And problem is formula for C tilde. Formula for B tilde is okay, inverse. We can take inverse of the exponent. Sum of two exponents is also okay, but 1 plus QB inverse of the 1 plus vertex operator, it's unclear how to act. I mean, this is infinite sum. So there's no formula like this. Instead, you can view this as some sort of the system of equations. So maybe I will not write the system of equation, but I state its existence and state how the answer looks like. So here we have P1, P2, P1 inverse. This is Q minus 2, P2 inverse. And so mutation is up to some detail is a certain operator intertwining operator which map X from Fock space which correspond to Heisenberg algebra B to Fock space which correspond to Heisenberg algebra called B. And since this is an intertwining operator, you can assume that it comes from some R matrix. And this is true. So this comes from R matrix for toroidal GL1. So if you start with a vertex which have loop to itself, this is literally Maulik-Okounkov Q-deformed R matrix. Or better to say, analog of the Liouville reflection operator, because now I act in one Fock space. And here, this is like more simple analog of the Maulik-Okounkov R matrix. So this is somehow correspond to GL2, and this is a GL1/1 analog of the Maulik-Okounkov R matrix. So formula which I wrote here, they're partially not true, partially don't have make sense, but it can be replaced by some avatar from the mutation theory. Okay, I have more or less 0 minutes, so maybe it's good time to give you a plan of my talk. So keywords which I haven't mentioned are screening operators. And maybe from the mutation theory point of view, this is the main meaning of what's going on. So the combinatorics of the screening operators can be traded to combinatorics of the cluster varieties. This is technically what's going on. I haven't told you about any geometry, like surfaces and so on. For example, you can ask me whether pentagon identity holds for these mutations, and it holds in some. It holds in terms of projective space sense. It's not identity, it's just transform. And we have something like 4 Crossley Poisson brackets, and so on. And maybe the very last thing which I write. Okay, maybe I say in words, and if somebody asks me, then I will write it on the board. In words, say the following. So one can ask, what is the reason? Why should I expect that some cluster varieties should be, even quantized, should have this chiralization? And of course, I don't know, but this is similar to the another known story that this cluster varieties for which we have this chiralization, they appear as Coulomb branches of four-dimensional series. And for Coulomb branches of three-dimensional series, there is very similar story that these Coulomb branches are associated varieties for some vertex algebras. And this is Q deformation. So instead of Coulomb branch of three-dimensional series, we have four-dimensional series, and instead of vertex algebra, we have Q vertex algebra. Right?
Are you done? Thank you so much for the talk. Okay, will there be any questions about the plan for the talk?
Yes, so one of the main advantages of cluster algebras is that if you have a Poisson cluster algebra, which is a relatively simple geometric object, then there is an automatic way to quantize it. Is this also the case in the chiral cluster world?
Okay, I don't. So here I already worked with quantization. Already started with quantization. So can I say that what is a good property of the corresponding Poisson bracket which appears as a limit? Maybe I don't know who would answer.
But usually it is hard to quantize things.
Yes.
Usually, I mean, in particular, in this quantum affine algebras theory, it's usually hard to quantize things because you have to kind of invent formulas. So Drinfeld made this great discovery of Drinfeld new realizations, which is really behind all this thing.
Yes.
And but for cluster algebras, quantization is an algorithm. So I was wondering if you could make this algorithm chiral, so to do it in the chiral world. Because Poisson story is much simpler.
Pasha is asking, do you have a Poisson analog of this?
Yes. We have Poisson analog of this. Yes. There is. Okay, I have to think. I'm out of time. No, good. Yeah, I have to see. Yeah, I see question. Yes.
Yeah, I think. Okay, one question.
What is the precise? Do you have a more precise statement about this relation with Coulomb branch and this Q vertex algebra?
What's precise statement? So
the kind of statement I have in mind for 3D was that the one you said for associative variety, and after you quantize, what the statement would be.
I don't know whether a notion of associative variety exists in this Q-deformed world. But so the statement that the variety which we chiralize appear as a Coulomb branches, it is either theorem or definition of what is Coulomb branches. So in BFN case, if you start with BFN definition, then it is. I mean, there are theorems that the corresponding Coulomb branches have cluster structure, and they heavily intersect with the cluster varieties which we chiralize here.
Okay.
But I'm not sure about name of the shade variety.
We need to stop here because we have the next talk without any breaks. But thank you so much for the talk and the answers.